All right, so this is going to be an example of a Bernoulli equation. This is the fifth problem on that set of problems I included on the week 5 recitation worksheet, on the last page of that worksheet. All right, so a Bernoulli equation looks almost like the form of a linear equation, except we can write it in this form, where now we've got dy dx plus p of x times y is equal to q of x times y to the n for some power n. So if we see an equation like this, and usually this is pretty distinct because you can kind of see, like, you're looking for that larger power of y. You let v equal y to the 1 minus n. That transforms our equation into this, which is a linear equation in terms of v and x. So then what you do is you solve this equation, resubstitute back, and then you can get an equation in terms of x and y, which represents your solution. So we want to solve this. So much like before, this isn't quite in this form yet. We want to divide through to get that y prime by itself. In so doing so, we get an equation of the following form. And now you can see this 2 over x would be my p of x. This 5 over x squared would be my q of x. So now we notice this is a Bernoulli equation with n equal to 3. So we're going to let v equal y to the 1 minus 3, which is equal to y to the negative 2. And so what this substitution does is it transforms my previous differential equation, this form, into dv dx plus negative 2 times p of x times v is equal to negative 2 times q of x, which would just be negative 10 over x squared. And so this negative 2, maybe I could follow through with it to simplify this equation a little bit, and this would be minus 4 over x times v. And so now you notice this is a linear equation. And so we can solve an equation of this form with an integrating factor. And so if you were to integrate that and sort of cancel out the e in the natural log, you should get that the integrating factor we want to use is x to the negative 4th. And so maybe on the integrating factor steps, I'll go a little faster this time. But remember, what we would do is we would take this x to the negative 4, multiply it on both sides of the equation. And so we would get that the derivative of x to the negative 4 times v is equal to negative 10 over x to the 6th. And maybe just for integration purposes, I'll make that negative 10 x to the negative 6. So now here we can integrate. And we get x to the negative 4th times v is equal to, if I integrate negative 10x to the negative 6, what I would do is I would add 1 to the power to make it x to the negative 5th, divide through by negative 5 to actually get 2 over, I'll just say 2x to the negative 5 for now, plus c. And so I can divide through by x to the negative 4 to get that v is equal to 2 x to the negative 1 plus c x to the 4th. But I need to substitute back, so this means that y to the negative 2 is equal to that. And this would be an implicit solution. If you wanted an explicit solution, you could solve for y. If you wanted to get y out of the denominator, you could do that too. I think the book takes like one extra step to get y out of the denominator, but this would be a fine implicit solution for that. So yeah, Bernoulli, basically you're just looking for that power of y for this form that looks like almost like the linear equation we had. And then what you're doing is you're kind of using this nice substitution to transform it then into the linear form, which we can solve. A fun thing to do actually is to work through the algebra, or the calculus, I guess, on that substitution and kind of work through why it works. I definitely enjoyed doing that when I was learning this, that took the derivatives, kind of substituted, and you can see where all of this comes from. So yeah, that is a Bernoulli.